So we're going to start off here at the institution, flying in to Bastwick Street. We're just there in Clerkenwell, but we're going to move over a bit further west to the current project, which is Old Oak Common over in the west of London. Now, unfortunately, I can't show you any pictures of Old Oak Common because they're not released until next week. Next week we have a big press launch and you'll be able to see all those lovely pictures, but you can't see them at the moment. So I can give you some tantalising details, I hope, about Old Oak Common. It is part of HS2. It's just on the outskirts of London, down there. But HS2 is a project to improve the capacity. HS2 is about capacity of the railway network rather than speed. People concentrate on speed, and it is a fast railway, but it is about capacity. The railway lines out of Euston up to Manchester and beyond are really at capacity. The number of people using the railway system has doubled over the last 10 years, and we desperately need more train paths to get these trains through. So we're building this new railway to improve the network, as shown there. The new high-speed lines go to Manchester and Leeds and York, and then they connect through to the normal conventional railway, allowing you to go further north to Scotland and what have you. Old Oak Common itself is a station kind of surrounded by railway. So the Elizabeth line and the Great Western line go through there, the yellow one from east to west. There's also the West Coast Main Line not far away, lots of overground lines, Central Line, even the Grand Union Canal, and railway depots. The whole place is surrounded by these railway infrastructure. That's the team building or designing it at present, and a few facts about it. We've got 8 ground level platforms serving Crossrail, the Elizabeth line as it's now called, and Great Western. We have 6 high-speed station platforms, and they sit in an 800-metre long, 65-metre wide, and 13-metre deep station box. Now, it's always good when you're a structural engineer to be able to see your projects out of a plane. I don't know if you've done this, you kind of take off in a plane, and as the plane flies over London or wherever you are, you can look out the window and say, look, there's my bridge, there's my railway station, there's my building. That's tremendously encouraging. Now, Old Oak Common, I've worked out, you will not only be able to see from a plane, I think you'll be able to see it from space. Right, so I worked this out this morning. If a number plate, the numbers on a number plate are 79 millimetres high, and you're supposed to be able to see them from 25 metres away. If this is 800 metres long, you should be able to see it from 250 kilometres away, which is well out into space. So that's a very encouraging thing about Old Oak Common. Slightly more prosaically, though, we have an enormous depth of London clay. This is one of the things I've learned on this project. I didn't know you got London clay that thick. It's 70 metres deep. It's hugely over-consolidated, and we have an at-rest earth pressure coefficient of 3. I didn't realise it went up that high, but it is a very high lateral pressure on our diaphragm walls and the props. So we've been dealing with the implications of that. We also have a 250-metre long roof, so there'll be a very impressive, large but economically designed roof above the station. And the whole brief is held together by a document that's called the Contract Requirements Technical Document, the CRT document, and we have to refer to this to find out what HS2 wants us to do with the station. Here's an extract, the structural bits and pieces, and you'll see down in the bottom right-hand corner that the structural engineers have to prevent pigeon roosting. Now, this is what gave me the idea of having unexpected education as my theme, because I've had to learn all about pigeons. I tell people I don't know anything about pigeons, I'm just a structural engineer, and they all run away and say it's your job, it's under the structural part of the CRT. So we have to learn about pigeons. There's one, so you know what they look like. And after some hunting around, we found that Syria produced a report called Invasive Species Management for Infrastructure Managers. And this tells you what to do with pigeons. It tells you not to feed them. If you do not feed your pigeons, they will not come, and then you don't have the nuisance. It's kind of like the opposite to graduate structural engineers. If you do feed graduates, they do come to almost anything. But pigeons don't come if you don't feed them. So that's what we're going to do, make sure that there's nothing to eat for them in the station. All the rubbish gets cleared away, bins get covered, and the pigeons will not come. But this is quite a thick book, so when you read through, you find out about more invasive species. One of them that caught my eye was the edible dormouse, which is a problem in the Midlands, evidently. Edible dormice running all over the Midlands. I did look at it and thought to myself, oh, I wonder what the recipe is for edible dormouse. Anyway, enough of Old Oak Common until next week when you can see the proper pictures. Let's go to Hungerford Bridge. Here's Hungerford Bridge in central London, the Millennium Project. Oops. Those are the people who were involved. We were the engineers. Westminster Council was the client. Lifshitz, Euston, Sandilands were the architects. And this gave us a link back to Brunel. It's quite exciting to have a link back to Brunel. We have that at Old Oak Common as well, because he built the Great Western Main Line. But here we had a kind of direct link back to Brunel, because he built the first bridge on that site. That's a suspension bridge that he built early on in his career on the site of Hungerford Bridge. And people could pay, I think it was a farthing, a quarter of an old penny, to cross the bridge, and it was a tremendously successful project in terms of finance. But it was soon bought up by the railway company, and those chains that held up Hungerford Bridge were recycled. They took them off to Clifton and used them in the Clifton suspension bridge. And here's a picture of that bridge being taken apart and the railway bridge being built instead. And the railway bridge started off with 2 tracks and gradually expanded. And this was the bridge we found when we arrived to start Hungerford Bridge. It was in a bit of a sad state, really. You can see some pigeons sitting on the pier there. Inside that pier was just full of dead pigeons. It was like a health and safety nightmare. If you walked around in it, it went crunch, crunch, crunch with dead pigeon bones. It was horrid. Also, in terms of structure, they recently repainted the bridge, so it was a quite a nice shade of green. But that panel of brickwork, that pale panel of brickwork, was not really brickwork. It was a fiberglass panel. They built a panel of brickwork and then cast fiberglass against it to make it look like brickwork. But it's gone pink because the fiberglass faded in the sunlight. And if you stood up there, you could kind of wobble it about because it wasn't terribly stiff. And then the brickwork down the bottom was falling off. So the railway bridge was in a little bit of a sorry state. And on the other side, there was this walkway which was just 2 metres wide. And there was a large flow of pedestrians going across essentially from Waterloo over to the city. And I always found that when I went, it was never sunny. It was always raining, and there was always puddles on the footbridge, and there were always more people coming in the other direction. So I always had to walk in the puddles. I don't know why it always worked that way around, but it did. So there was a challenge to improve that. And we entered a competition with the Staves and Sunderlands, and this is one of the competition drawings. And you'll see we proposed 2 footbridges, and then various extra pieces. The original footbridge had a river bus pier, so we wanted a river bus pier, and we rather fancied having a floating restaurant and some sort of low-level bridges. Some of those things disappeared with budget pressures, and so this was the final scheme: a bridge on either side of the railway bridge. And a kind of island with maybe a future diagonal link bridge at river level, which has never actually happened. Just notice on there the routes of the tunnels. We've got the Northern Line tunnels on the bottom of the screen, the Bakerloo Line tunnels on the top, and then running top to bottom on the right-hand side is the District Line. Lots of tunnels under that part of London. We'll come back to that in a minute. Our first real challenge in designing Hungerford Bridge, and the first thing we learned a lot about, was ship impact. These days you can look in the Eurocode and it tells you what ship impact forces to use. Back in the 1990s we didn't have a Eurocode, and we had to work it out from first principles, basically. The Port of London Authority told us we had to allow for a 3,000-ton boat travelling at 12 knots, 12 nautical miles an hour. This was the closest thing to that. This is called the Tracey Bennett, and and the Tracey Bennett weighed, I think, 2,400 tonnes and carried gravel from the North Sea upriver to concrete plants. And this is the Tracey Bennett returning back to the North Sea to get another load of gravel. So you can see it's quite high out of the water. And we had to work out if that vessel went out of control and hit our bridge, what the load was. And we used a tremendously clever guy called Bruce Nicholson, who we worked with for some time. Sadly, he's no longer with us. But he was tremendously clever. And we'd ask him to solve problems, and he'd come back with like 4 handwritten pages of calculations, which would really sort of nail the problem. You know, sometimes you ask people to do that, they give you a book of computer output, or they write you a very long document, or there's pages and pages and pages of calculations. Bruce could do it in 4 sides of A4 and really sort things out. And the way he did it was to get hold of the construction drawings for the Tracey Bennett, and estimate how much of the steel in the front of the boat would be crushed in an impact, and then how much energy that would absorb, relate it to the kinetic energy of the boat, and that would give him a force. That sounds tremendous. That sounds very simple. It took a long time to get there, but it was distilled down to, as I say, 4 pages of calculations. And we came up with a force diagram like this. So 30 meganewton impact force on the bridge. Now, I think the Eurocode gives you a smaller number, but we think our number is right. Okay, and that's what it looks like in real life. Slightly depressingly, we had to think about bombs. That bombs will keep coming up. I've learned quite a lot about bombs, and I'm not sure I really wanted to. But here's the first stage. We knew that Hungerford Bridge had been hit by a flying bomb during the war. And took out one of these spans. They did restore the railway service tremendously quickly. They rebuilt it. I think given by the position those guys are standing, they didn't have a lot of safety regulations to worry about, but it was wartime, and they repaired the bridge, got it all back working, and happily it destroyed those kind of secondary beams, but the primary trusses were okay, and the foundations were okay. So it could have been a lot worse. We learned about the different sizes of bombs that were dropped in the war, and you can see things that range from 50 kilos to 1,800 kilos of explosive. And I find it slightly depressing that they give them sort of joke names. So number 7 was called Herman, number 8 East, or number 9 Fritz. And I really do. It's a bit of an indictment on humanity, really, that we give joke names to these things that kill so many people. We learned that bombs don't just fall, if they bury themselves in the ground, they don't just form vertical holes, they often have this J-shaped trajectory, so they kind of go laterally. So if you find a place where a bomb has hit, that's not necessarily where the bomb is in the ground. It can go kind of sideways. And so there could have been bombs buried underneath the railway bridge, even though there weren't any sort of holes in the railway bridge to indicate their presence. The other depressing thing about them was that some of them had timers in. So the idea was that they'd drop a bomb and it wouldn't go off. It would have a timer in it, and while people were clearing up the bomb site, the bomb would then go off and kill all the rescue workers, which again is a bit an example of man's inhumanity to man. And we became concerned. You remember all those tube tunnels on the bridge? We became concerned that either the piling plant would set off a bomb, or the piling plant would cause a bomb that hadn't gone off, that had a timer in, to go off. And people said, well, what are the chances of that happening? And we had to work it out. And we engaged a guy from the Atomic Energy Authority who did this calculation of all these things that had to happen for a bomb with a timer on to go off. And you can see it comes up to quite a small probability down at the bottom right-hand corner, 7 noughts, 3 essentially. And we thought, well, is that good or bad? That sounds a fairly low probability, or are we going to worry about it? And then we thought, well, if it does damage the tunnel, the river is going to flood into the Northern Line or the Bakerloo line, and then that will flood through into embankment station, and then it will go into another line, and then in another line. And we wondered how many people that might affect. And if it happened in the rush hour, well, anybody knows what might happen. But we said, we used this technique called a fatal accident rate. Somebody called Edmund Hambley, a guy who wrote a book called Bridge Deck Behaviour, quite a famous bloke, produced this way of comparing risks that he called the fatal accident rate. And basically it's how many deaths you'd expect if people spent 100 million hours doing an activity. So that might be rock climbing, riding a motorbike, walking to work, or putting foundations in Hungerford Bridge. So we worked it out. We said we were actually spending 1,344 hours, and there was a probability of disaster of 0.703, and we could work out a different probability if we'd spent 100 million hours doing that, and how many deaths we estimated quickly because we didn't want to think too hard about it. And that gave us a fatal accident rate of 200. And for comparison, that's not as bad as riding a motorbike. Riding a motorbike is, apart from it flying a helicopter, is about the most unsafe thing you can do. It is worse than smoking, though. If you spent 100 million hours smoking, that would be quite an effort, but it would cause 40 deaths. And the tolerable limits vary according to whether you're in charge of the risk or not, but the tolerable limit is 1. So we decided that was not acceptable. We could not accept that risk, and so we had to redesign the foundations of the bridge. So here they are initially. There's piled foundations. One of them is up against the riverbank, and we changed it over. We moved that pylon onto the riverbank and used caisson foundations so that people could go down the caisson, sweep with a metal detector for the bombs, and then dig down. They could sweep like a 3-metre depth of soil, and they could dig down another metre and keep going ahead until they built the foundation. So it was a major change to the bridge, but that was in response to this risk that we were concerned about. We didn't know there was a bomb there, but we were dealing with a risk of something. So that was a fairly major change. Another thing we learned on Hungerford Bridge was how to deal with cables. It's got lots of cables. Hungerford Bridge, I think there are 32 cables on every pylon, and they look like that. And the pylons were lifted in by a very large crane. I'm just showing you a picture of a very large crane there because I do like very large cranes. They come together at the top at a thing we call the angel wing, which I drew the original drawing for this on my kitchen table. It was refined a bit later, but it's still quite large. That's where all the cables come together. They weren't cables, sort of spiral wound cables. They were McAloy bars. And the first thing I learned was that you can't just pick up a McAloy bar. You can't pick it up by the end because the self weight will cause it to sag, and then it will kink. When the bending moment gets sufficiently large, it kinks, and then you can never get the kink out. And so what you have to do is pick it up with a strong back like that. So you support it along its full length, and then fix it at each end, and then you take the strong back away. But with Hungerford being a very redundant structure, we had to tension all these bars up and make sure we had the right tension in each bar, being aware of the fact that every time you tensioned one bar, it affected the tension in all the other bars. And we used these things from McAloy called Techno Tensioners, sort of hydraulic things that would pull on the bar and allow you to do up the turnbuckle. And they were calibrated, so you could measure the tension using the Techno Tensioner, but it was quite an awkward thing to move from one bar to another. And we needed a technique to measure the tension without using a Techno Tensioner. And we thought of strain gauges, but they weren't very reliable. They kept falling off. They didn't give us very good readings compared to the Techno Tensioner. And then somebody, it might have been me, but I'm not entirely sure about this, remembered the equation for a guitar string. If you know the mass per unit length of your guitar string, how long it is, and the tension in the guitar string, you can work out the frequency of the note it will play. Sadly, guitarists do not use this formula. I don't know why, but we could adapt it, because if we measured the natural frequency of the cable, and we knew the other things, we could work out the tension. And then we tested that against the Techno Tensioner and found that that frequency method was much more accurate than the strain gauges. Some of the strain gauges were okay, but you can see some of the yellow bars there for the strain gauges were much different from the Techno Tensioner and the frequency method that are quite close together. The other thing we learned was, you might have done this at university, you learn about eigenvectors and eigenvalues, and you learn how if you shake one part of a structure, sometimes it sets off another part of a structure, even though the bit in between is not actually moving. Now, your computer will tell you that. You put the structure into a computer program and set it to create, work out the mode shapes and the natural frequencies, and it will show one piece moving over here and another piece moving over there. And I always looked at that and thought, yeah, I bet that doesn't happen really. That's just the computer. And how can it move over there and not move in the middle and then move over here? Well, on Hungerford Bridge, you can actually see that happening. So if I can get this video to work. Here's a disreputable character going out on Hungerford Bridge, shaking that cable. And then when you move over to the other side of the bridge, there's another cable which I hadn't touched, shaking away. And if you find the right cable, you can shake one cable and other cables 2 or 3 pylons down the, sort of 200 meters away will start to shake. It's a very impressive trick if you want to show off some engineering, unexpected engineering to schoolboys or something. This isn't really education, but I'll just tell you about this. The client, for some reason on Hungerford, decided that we should organise the opening ceremony. I don't know why, but they did. They asked us to organise the opening ceremony. It was written into our brief that we would organise the opening ceremony. So Liftshire Staves and Sandilands drew up this plaque here. This was to be provided for the opening ceremony. And I went to a client meeting one day, and the client said, well, we'd better book up a member of the royal family, because they do get booked up a long way in advance. We need a member of the royal family to do this. And I said, no, I'm sorry, look, I've got to organise this opening ceremony. I'm going to get my mum to do it. And so we got this thing, and I said, I'm not having that. I crossed it out and wrote Mrs. Muriel Parker on it. And sadly, this was actually the contract set I'd chosen to mark up. And when you went out on site, there were all these copies of the contract set lying about, and everyone had an opening ceremony plaque with Mrs. Muriel Parker. So everybody on site knew that my mum was supposed to open the bridge. She didn't actually open it. Princess Alexandra opened it, but my mum did get an invite to the opening ceremony. So that was a result. Anyway, enough of Hungerford Bridge. Let's go off to St George Street, which is just behind Oxford Street, and a little building, 28 to 29 St George Street, near Hanover Square, next door to St George's Church. And this is a very small building, but it's interesting in a number of ways. One of them is that it's a scholarly replica of what went before, which is a nice way of saying it's a bit of a fake, really. But inside, it's that's the building on the left there is the building it's a scholarly replica of. This is from a watercolour the architects found from 1800 and something. And on the outside, it looks like a Hanoverian building on, let me get this the right way around, Hanoverian on the right and Georgian on the left. And round the back, there's an extension, or it looks like there's an extension made in Victorian times. On the inside, it's an open plan office building with cellular beams that span from perimeter columns to a concrete core in the middle. But on the outside, it looks as though it's been there for hundreds of years. And we learned a lot here about bricks. The older bricks on the left are larger bricks and have a thinner joint. This was when labour was cheaper and mortar was more expensive, so you used a thinner joint, and the bricklayers had to choose the size of bricks to keep the brick courses level, despite having a very thin joint. So they're only 5mm joints. When we went to the Hanoverian side, we had 8mm joints because they decided they could spend a bit more on mortar but save on labour And now, of course, we have 10 mil joints because we want to save even more on water. You'll see on the right-hand side, the bricks are sort of mottled in colour. That was because people would often use the bricks that had been at the sides of the kiln where they'd get burnt. So our architect specified that he wanted burnt bricks that had been at the side of the kiln. So even though they're handmade, they were burnt, and that gave us the difference in colour. The things under the windows are called swags. I didn't know that before this project. And those lions are all individually carved, and there are 4 of them altogether, and we had 4 different stonemasons carve them from a sketch, so they all came out slightly different and looked authentically old. And then finally, we wanted the stonework to look old, and the architect wanted to paint it with yoghurt, so that microbes would grow on the stone and it would look sort of mottled and old. We didn't have time for the microbes to grow, so we used a sort of stone paint instead. But nevertheless, it was quite an impressive aged structure when it was built, brand new, in the early 2000s. Inside, there's a spiral stair, and this is one of those cantilever stairs or torsion stairs. It's a kind of modern take on that, so it's made out of precast concrete, and we devised this system to bolt the torsion pieces down into the precast walls, and that rises up. And it's 6 stories tall. The architect told me that it's the tallest cantilever stair in London. I'm not sure whether that's true, but it's certainly quite a tall stair. And down the middle, it has this kind of string of lanterns, brass lanterns. Now, normally we don't get involved with lantern design, but unexpected things happen in structural engineering. And the contractor phoned me up because the original design for the lantern had all the weight taken by those sort of curly brackets at the top. So there's that sort of circular, or almost circular piece around the top of the glass, and there's those 5 curly brackets that meet at that central sort of boss thing, and then the load went into that chain. Well, that was kind of okay for one lantern, but by the time you'd strung 5 of them together and they weighed half a ton was going through those curly brackets, which were brazed on to the brass piece underneath, and it really didn't look safe. So I had to work with the lantern maker to put a threaded rod down the middle in a way that couldn't be seen by the people who used the stair. And this was great fun because we worked with this guy called Ronald Sitch, who never actually told me his first name. He was always just Sitch. He used to phone me up and say, "Sitch here, I want to talk about this lantern." And I'd have to go down to Soho. And he had a workshop in Soho, which was like something out of Dickens. It just sort of went back. There was a little shop at the front, and it just went back and back and back. And there were people pouring molten metal out of ladles into casts, and hitting metal on furnaces and forges, and brazing things together with gas flames, and all these tools everywhere, and half-built chandeliers and things. It was an amazing place. Sadly, it's closed down now. Mr. Sitch died, and his sons, who'd worked in the business, decided they didn't want to carry on. So it's now closed, which means that if you want to get a light fitting in the shape of a brass pelican, you'll have to find somewhere else to go, I'm afraid. So let's move on now. Let's fly across town again to London Bridge Station down there in the southeast. So London Bridge Station is a project we worked on in a joint venture this time with Arcadis. Worked for Costain and Network Rail. Grimshaw's were the architects. London Bridge was the first railway terminus in London. Back in 1836, they built a railway line from Greenwich, and they built it on arches, so it was out of the way of the roads going underneath, and they experimented with all sorts of different ways of supporting the track, some of which were very bumpy. They thought one way to do it would be to have longitudinal sleepers, stone sleepers, underneath the rails, and they tended to have hard spots over every pier on the viaduct, so the train sort of bumped along, and it took them some experimentation to come up with a smooth ride and a better support system. There was a lot of opposition. I don't know why people oppose railways, but they do sometimes. What they don't do quite so much now is write music hall songs against them. And Mr. Schillerbeer, who ran the Schillerbeer's original omnibus company, commissioned this music hall song, which I'm not going to sing for you, but I kind of imagine this would have been sung by a large woman with a hat with artificial fruit and birds on it. But unfortunately for Mr. Schillerbeer, his propaganda didn't work, and London Bridge was a terrific success, really, and it was expanded and expanded very quickly over the course of the years. So the sort of top left is how it was in 1836, and very, very quickly it expanded to fill the whole a very large site, and they kept adapting it to cater for it. The thing was, though, that it was always two stations. There was from quite early on, there were through tracks that went through to Waterloo East and Cannon Street, and there were terminating tracks, and they were run by rival train companies who weren't really interested in giving business to each other, and so they were a bit disconnected. And although British Rail made some noble efforts to unite the stations, it was still quite difficult to find your way from one part of the station to another. It was not an easy station to find your way around. It was also, here's some more bombs, it was also knocked about a lot in the war. So the train shed down there at the bottom was hit by lots of bombs, and you can see from this RAF kind of reconnaissance picture that there was a lot of bomb damage done. So that train shed, some of it was original when we arrived, some of it was replaced after the war with aluminium trusses. Here's a wartime bit of temporary works to hold it up while they repaired it. Slightly worrying looking temporary works. In the 1980s, it had an extensive refurbishment, and they built this space frame roof on London Bridge, which was designed by computer. It must have been one of the earliest structures to be designed by computer. But it was designed in the days when computers just produced numbers, no graphics, just numbers. And so somewhere we've got some record calculations where somebody has drawn the space frame by hand and then plotted the bending moments on the space frame by hand using the numbers from the computer program. But despite all that effort, they did do a remarkably good job. So when we back analysed this space frame, we found that the utilisation factors in all those little spindly members were very close to 1. They'd done a terrific job to optimise the amount of steel in it. And the space frame covered up the concourse, which originally was quite spacious, but over the years began to be filled in, and people built retail in there. The Jubilee line came along and put some escalators in the middle, and it became quite a cramped and pretty unsafe place to be because there were so many people squeezing into such a small space. And our job was to redo the station, provide more train paths so that Thameslink could take their trains through, and altogether improve the circulation through London Bridge. So there's the station as it was in just after 2000, I think. And here's the roof as it was in 2012. So that's the other way round to that aerial photograph. And you can see the train shed at the bottom. The space frame is just above the shard there. And then there are canopies, part-length canopies over the platforms. And we took away the train shed, and we took away the old canopies, took away the old platforms, and re-spaced them so that we could sort out the widths. When you look at this old picture of the platform, some of those spaces are very tight. So if you look at the top platform there was a very narrow space between the stairs and the edge of the platform, and it was not at all safe in the rush hour. You were kind of standing with your back to the stairs, and the platform edge was very close. So we used some of the spare space there, respaced out the platforms and got a much better arrangement. Down below, as I said, the railway was built on arches, so there were arches everywhere. They didn't seem to take much notice of the arches that were there previously when they built a new set. So the spans kept changing. The piece through the middle with the small spans is the original railway, and then they decided they could have larger spans, and then sometimes they built them at different angles. Sometimes they actually turned the spans through 90 degrees. Nothing seemed to match up, and if you walked through those arches, sometimes you'd walk through and there'd be a pier in the middle of the arch because the next set of arches didn't really match up. Anyway, there were all those arches, and we took away a big space in the middle to create a new concourse. So we have a concourse that's 130 metres wide, 70 metres deep. We always say it's big enough to fit the pitch at Wembley on it. There's a few columns that would get in the way of playing football, but it is a big concourse, the biggest concourse in the UK. And for the first time, it links together all those platforms. So where the Victorians had rival railway companies that didn't really talk to each other, we now have this concourse, so everybody can come down off the platform into that same space, interchange between trains, all linked through to the underground. Here's some of the arches. We learned a lot about arches on London Bridge. So there's one of the arches. You can just see in the background, that's one of the ones with a pier in the middle of or a pier of the next lot of arches in the middle of this one. Some of the arches were a bit of a strange shape. Here's one that's not exactly symmetrical. Happily, that's one of the ones that got demolished. We had one arch that was completely filled with concrete. Nobody really knew why. We suspected it was wartime damage, but it was filled with concrete. We did do some investigation to try and find out how thick the concrete was, and somebody went down on site with a guy with a drill, and they drilled in, and the guy kept putting more drill bits on, and after he got to 4 metres, he said, "I think we'll stop now because we'll be coming out the other side." So this was a drawing we did to show how that arch could be rebuilt as a proper arch, so it could be a retail unit and not just a lump of concrete. And this, as you can see, there's lots of notes in this drawing, lots of ways telling them how to do it, things they must take account of, ways to do the timber centering and so on. And we gave this to the brickwork specialists. I think they just ignored it, and they knew what they were doing, building an arch. And they used polystyrene centering, not something the Victorians would have done, but that's the way to do it nowadays. And these guys built a lovely arch, which is down there. You can't actually tell the difference between that one and all the others now. We had to create openings. We had to learn how to create substantial openings through the arches while the trains were still running. And this is one of the more heroic ones. This particular one was quite a tall opening, so it had to go through above the springing point of the arch. So we had these temporary frames supporting the arch. There were trains running above this at the time, and then we introduced a kind of picture frame inside the temporary supports and then cut the temporary supports off. You might wonder to yourself why we put that opening there when there was an opening on either side that we filled with concrete. Just wonder that to yourself. I'm not going to tell you. Up above ground, there were canopies, full-length canopies on all the platforms. So all the platforms were realigned and new full-length canopies on every one, which we developed with Grimshaw's. And we wanted to make sure they were built efficiently and safely, so we built a prototype up at the fabricator's yard in Yorkshire. So here's the canopy prototype, and we used this to test the method of construction and make sure it all went together properly and make sure the guys knew how to do it, and also testing the access to the service routes. There's lots of services concealed in that canopy, and we wanted to make sure that it was easy and safe to maintain those services, so that was tested out. There's also precast platforms down below. We tested that in the same prototype. We did an earlier prototype as well. This is the early prototype. This isn't actually made of steel. This is made of MDF, and it was made in Edmonton, I think. And this was just to see what the thing would look like. And the clever thing about this was that it was all done with mirrors. There's only part of a canopy built here, and there's a mirror down the centre line to make it look twice as wide as it should be. And then there's a mirror at each end, so it looks almost as long as the true thing. And you can see some of those guys in blue hats appear several times because of the mirrors. But it was a wonderfully effective way of mocking up that canopy so that the planners and Network Rail could see what was going to happen. Further down, we rebuilt some of the arches, and we wanted a kind of modern take on the quadripartite arches. Quadripartite arches are arches that go in 4 directions, so it's like 2 barrel vaults intersecting with each other on a grid, or a grid of barrel vaults really intersecting. But we wanted a modern take on that. We felt it probably wasn't realistic to get it done in masonry in the time available, so we wanted a concrete one. And it was decided to use a board mark finish. Now that hasn't been used a lot since about the 1980s. It has been used in this building at the institution. We were kind of developing this in parallel. We went for a slightly different finish, and we did lots and lots of trials. These were trials of different sorts of board mark finish. So each side of these things were called tombstones, and they were built in the old London dungeon arches. I often wondered if passers-by overheard us saying we're going to look at the tombstones in the dungeon, what they would be thinking. So each side of these tombstones had a different finish from different species of timber, different roughness, different surface treatments on the formwork, to see where we'd get to. And eventually we settled on, I think it was the smooth planed Douglas fir, I think it was, to be the thing we wanted. We found that the pieces of timber were all within the tolerance that's specified for timber supply, but it was a bit too much. And you got this lipping. You can see down on the bottom right, there are shadows there because some bits of timber are narrower than others, and the surface was lipped, and that wasn't the impression we wanted. So we had kind of close tolerance timber formwork, so that we didn't get so much lipping. We had a much smoother surface. And we built another prototype. Here's a prototype being built in one of the arches. Had a sort of polystyrene former to form the shape at the top. And then the timber formwork was external, and we pumped self-compacting concrete into that to create the thing. Unfortunately, the prototype had a smooth panel on the side nearest that you could actually take a good photo of. So we decided that a smooth panel just wasn't what we wanted, because you could see the lines between the panels. So we ended up with this, which I think looks quite good with those. That kind of subtle timber formwork. Here's some more pictures of the station. These are the bridges that take the trains across the concourse. There's the concourse itself. An open space in the middle. Bollards here to deal with vehicle-mounted bombs. More bombs, I'm afraid. And seats as well. Massive concrete seats on the north side. Now, we're not going to go far away for the next project. Here it is next door. It's the Shard. I was the lead engineer for the Shard, and these are the people involved. So WSP, the structural engineer, Renzo Piano was the architect, and Seller Property were the clients. It is what they call the vertical city, so there's different things happening at different levels, and that explains the tapered shape of the building. So you have big office floor plates at the bottom, because people on different floors don't talk to each other very much, so it's good to have a big floor plate to get as many people as possible on one floor. And then as you go up, the restaurants, it's good to be quite near the facade and see the view from your restaurant table. You certainly want a view from your hotel room, and then above that there are apartments, and you can walk all the way round in your apartment and look out. And then right at the top there's a viewing gallery where you can pay and see a terrific view. But I'm just going to concentrate today on the spire, which is up above the viewing gallery. It provides the final kind of pinnacle on top of the shard, and I'll just talk about that. Now, it's a steel-framed thing. The shard is interesting in that it's steel at the bottom for the office buildings, then it goes to concrete for the hotel and the apartments, and then it's steel again for the spire. And we had a design that looked like this. And initially, the contractor said he was going to build it piecemeal. In other words, he was going to lift all those pieces up in bundles, form some kind of temporary platform, and erect them one by one in the spire. And we didn't think that was a very good idea. So we devised this sequence with modules to build it. And these are the original sketches I did on a design development note to show how that could be built in modules and form the thing. So we went from that to modules like that. Not quite the same modules that I came up with, but it was my idea, right? So we erected all the number 1 modules first, and then the 2s, and then the 3s. And these modules were fabricated in Yorkshire, brought down on a truck. They were as big as the truck could handle and as big as the tower crane could lift. And then they could be lifted up. The truck would arrive, they'd attach the chains to the module, lift it up, bolt it in place, and get the hook back down to ground level, and that was a 20-minute cycle. So when the weather was good, it was a very quick thing to build. Again, we did a prototype. We did a trial erection, in fact. This is the real spire, but it's being erected in Yorkshire as a kind of training exercise and a way to refine the details. And that was a way of we weren't doing this at 250 metres above the ground. We were doing this at, obviously the bottom is at ground level, but it was a much safer way of testing out the systems and training the people to make sure that it could be built safely and efficiently when they finally got to site. So that's the bottom third of it. There's about 20 metres height there, and that's the top third being built. It's quite an expensive thing to do, but it was very worthwhile in terms of programme and safety. And up at the top, you sometimes got views like this. So this was a day when the cloud base was below the top of the shard, and there were guys erecting steel here. So the steel was coming in and being rained on, and then they'd lift it up, and it went through the cloud and into the sunlight, and the guys at the top were out in the sun putting it together. Now, we did learn a lot about the weather on the shard. So when you went in to the site, this was the first thing you saw as you went in. This board, which gave you different readiness levels, which related to the wind speed. And so this particular day, we're on yellow alert, and there's some restriction on what you could do, but it could get into different colours. And obviously, if it was, I think there was actually a black alert as well, where you just sort of sat in the canteen all day. But this was a real issue because it's such a high building, and if you drop anything or if anything gets blown off, it can have severe implications. So they kept a good eye on the weather. And we spent a lot of time early in the project wondering how much downtime there would be because of the wind. And at the beginning, nobody really knew. And this was the graph that the contractor finally came up with. So the grey piece is how the building was built. It's the height of the building with time. So it's going up from 0 in January 2010 and finishing at 310 metres in 2012. And as we went up, this is the amount of downtime we were getting from the crane. So as you'd expect, you get more downtime the taller it gets, and then the peaks come in the winter. So we got the worst downtime in January 2012 when we hardly were able to use the cranes at all. And then in the summer before, even though the building was quite tall, it was less. Now, I mean, those are trends you would expect, but we didn't know the data before we did the project because nobody had built anything that tall. Sometimes you'll go to you'll look at the shard and you'll see that the top disappears into the cloud. This is a day when you get a free ticket for another day at the viewing gallery. At some stage, I think it was Bloomberg or the New York Times printed an article saying that if you bought an apartment in the Shard, 33% of the time you'd be in the cloud and you wouldn't be able to see the view. And Irvine Seller phoned us up about this and said we'd got to find out about it. And it was sort of, another bit of structural engineers being asked to do unexpected things. How could we, what would we know about clouds, So my colleague Bill Price got onto London City Airport and got hold of some data. And this was their data for the 6 months before that, how much cloud there was below, the number of days of cloud per month when the cloud was below 150 metres. And from this, we worked out that we'd probably get about 64 hours in the winter months, which is, that's a bit of cloud, but it's nowhere near the 33% that the newspaper had reported. So we could at least give Irvine the statistics about the weather, even though we couldn't change the weather for him. And then I'll finish off by just telling you a bit about the cranes, because we do like cranes. So we had tower cranes, obviously, to build the thing. The crane at the top there went up with the slip form, which was a world first. So it went up continuously instead of being attached to the concrete and having a sort of stop-start method where you lift the crane and then run the slip and then stop the slip and lift the crane again. So this was attached to the slip and went up continuously. But when it came to build the spire, that crane was in the way. So what we did was we used that crane to build another crane on a bracket on the outside. The bracket was supported at level 52, stayed back to level 72. And you can see this picture was taken on the 3rd of July. And that's quite an unsafe way for a tower crane to be. There were 2 tower cranes there, and if the wind had blown, one of them could have swung round and hit the other one, and that wouldn't have been safe at all. So we could only do this at a weekend when there was no wind predicted for 48 hours. So happily it was the weekend we wanted, and you can see it's a lovely day, and they used the crane on the slip to build the crane on the bracket, and then immediately, like the very next day, the crane on the bracket took down the crane on the slip. So then we could use the crane on the bracket to build the spire on the top of the building. After a bit though, we had to get rid of the crane on the bracket once the spire was finished, and that could kind of deconstruct itself, bring itself down. But before it did that, it built another crane, a recovery crane at level 72. So the crane on the bracket built the recovery crane, and then the crane on the bracket kind of deconstructed itself, and then the recovery crane took down the crane on the bracket. Of course, this left us with a recovery crane, and we had to bring in a spider crane, and the spider crane was lifted up there and took down the recovery crane. Well, of course, that left us with a spider crane, and we kind of thought this would go on for a long time until we were left with something made of Meccano that worked with string. But unfortunately, the spider crane went down in the lift. There are still cranes up there. There's a building maintenance unit up the top to do glass replacement and cleaning and what have you. And then this is just a video of that crane on the bracket lifting in. This is the last piece of steel to be erected. We had vertical modules as well as horizontal modules, so it's lifting in that last module. The client's definite aim was for the contractor to be finish the steel, finish the glass, get the tower crane down before the Olympics. They did not want the Olympics commentators to show a video of a helicopter flying up the Thames and then say, there's the Shard, it's not finished. They wanted it finished for the Olympics. And so this happened in April, so we were in time, and sure enough, it was finished for the Olympics. You'll see some pictures of people higher up than I would like to be. So while that, I'll now show you just a few pictures. Really, I'll just kind of sum up. I just hope that I've been able to get across what a great job it is to be a structural engineer. I mean, you work on these wonderful projects, you have a positive effect on people's lives, and we have a privilege, really, in doing our work to build these things. And there they are, they sit in the city or out in the countryside, and we have a privilege that we're involved with them. But we also have a responsibility. We have primary responsibility in terms of safety, talked about that with that trial erection of the spire. We have a responsibility in terms of use of resources, not using too much material for environmental reasons as well as economical. And we have a responsibility for appearance. It's not just down to the architect, it is down to us to put things together in such a way, to build the bones so that the body can look good, sort of thing. So we have that responsibility. But it's not all serious. We do get a great amount of enjoyment out of it. There is a fun of learning about these things, about learning about the engineering, about ship impact and, cables and cranes and that sort of stuff. And also the unexpected things you get to learn about I don't know, pigeons and clouds and lanterns and all that business, things you don't expect to learn when you start off on a project, and that's great fun. So we do work on great projects. We have that sort of engineering mindset where we start off with incomplete data and we have to come up with an elegant and an economical and a safe solution. But we do work on these great projects. It's a great privilege to do it, and even though it's quite a responsibility, it's also great fun. So, if you're chasing up a bad debt or thinking about a partial safety factor or maybe having a difficult meeting with a client, just remember the privilege you have as a structural engineer and the responsibility and the enjoyment and the unexpected education. Thank you very much. So we can take some questions if you like. Rachel's got a roving microphone, so... do
you have a favourite project, John?
Will you use the microphone and then you get recorded on the...
Okay. Out of all the projects you've done, do you have a favourite one?
Well, it's got to be the Shard, because it's visible from everywhere, and not just from a plane, but... and it was great fun to work on. On the whole, we got on with everybody on the job, and that makes a big difference, the people you work with. And on the whole, it's a well-loved project. People are... I took my sister and her family up there last weekend, and they were excited to go, and so it has to be that one. They're all good in some ways, but that's...
Supplementary, and by your calculation, how far away can it be seen?
I'll leave you to work that one out yourself.
Are there any designs you think you could have done better? Like, looking back, you think you could have...
No.
You think you could have changed it?
Yeah, you always look back and think, how could I improve that? We wasn't in this talk, but we did Canning Town Station on the Jubilee Line extension, and we had to fit in a viaduct for the Docklands Light Railway. And we were constrained because we had overhead power lines from between pylons going above Canning Town, and there's a safety zone around the power lines, and then we had 13 millimetres between the edge of the safety zone and the top of our canopy. So we had no extra space at all. So we had to devise this viaduct that could be kind of slid into place, built away from the power lines and then slid into place. And we did a glued segmental viaduct. And every piece was, there were precast elements and every piece was different. And that didn't feel quite right that they were all different. And I've often sat there thinking, I wonder how I could have done Canning Town better. I've never actually managed to think of a way of doing it better, but I'm maybe we could have done, I don't know.
talk about London Bridge and the history there. I was just thinking about Euston. Are we going to end up with a similar issue?
What, dealing with history?
Well, there's the HS2 and there's the Network Rail site. Historically at London Bridge you had the two competing teams who didn't want to talk to each other and didn't have a joined up station.
Well, we did some work on Euston a couple of years ago, and certainly the intention is to have two stations that work together. Of course, at London Bridge you come in on one train and you might change to another train and go somewhere else. That's less likely at Euston because you'd be coming in from the north, changing trains and going back north again. So it's probably not quite such an issue, but we do have to integrate with the underground, and there's a lot of effort going into improving Euston Underground Station. I know at the moment you go to Euston and there are every underground platform has one main entry place, and HS2 want to double that, so every underground platform will have two entry places to improve the flow of people. Yeah, it's always a challenge though to adapt these stations and keep them running and deal with the flow of people. Okay, right, thank you very much. Oh, one more question there.
I was just going to say that it's been...
Quick, towards the microphone.
It's been fascinating, thank you.
Thank you.
You learnt a great deal, and we've learnt a great deal as well of the things. Do you feel that your clients learnt in the same way? Do you think we were able to communicate the sort of things that we came up and we solved in the way? It was just a case of, oh, well, they're just doing what they're employed to do.
Ooh, that's a difficult one. I think so. In some some things you learn about, and the client for that project in St George Street was very interested in all the bits and pieces, and I have the brochure, the kind of marketing brochure, and he'd obviously been very interested in making it look like an old building, so they'd bought second-hand stone to put in the lobby, and there's a desk in the lobby, and the desk is covered from leather that they'd recovered from a U-boat that sank or something. So this leather had been sunk in the Baltic for 30 years, and so he was very interested in all that old brickwork and how can we make he was very keen that the sash windows look like single glazed. Well, they are single glazed sash windows, but they wouldn't comply with building regs. So the architect came up with this double glazed panel that sits inside the sash windows, but the frame of the double glazing is not visible from the street. The glass goes all the way out past the edge of the window, and the frame is kind of inside the office, so that when you look from the street, all you can see is the single glazed sash. You can sometimes pick up the reflections, but and he was very interested in all that sort of thing. The client on Hungerford Bridge was interested in ship impact, but only because it kept putting the budget up, because it's such a big force you have to deal with. Okay, all right. Thank you very much. Thank you.